Okay, so thank you everyone for coming. Today I'm going to be talking about Martian spacesuits and kind of going over the technologies that we're going to need to perform Martian EVAs. My name is Will Green. I'm a PhD student at the University of North Dakota. Speaking of the ARG missions in ILMA, I was the maintenance man for ILMA throughout most of COVID. That was very fun. So I've also, right now I'm working on collaborating with, for my PhD research with the Anthropometry and Biomechanics facility down at Johnson Space Center. I also was able to do an internship tour on the XEMU team working on the EPG, which is the outer layer of the spacesuit. I've done work on 3D printable spacesuits, dust mitigation. I made an exoskeleton for our research lab and a couple other fun things. So let's get started. So a little bit, just starting to think about how you design a spacesuit and where do you start. So first, you're going to have a mission profile, which is kind of like where you're going, how long you're going for, and stuff of that nature. And then, in addition to that, you're also considering where you're going. So you're going to be in lunar, like on the lunar surface, the Martian surface, or microgravity. And a combination of those, you can then derive a set of requirements. Those requirements are then going to be met by a series of technologies, which will then be incorporated into your spacesuit design. So I'm going to kind of go over the different mission profiles we can expect to see for a Martian mission. A little bit about the surface of Mars, the operating conditions of the spacesuits, and then as a result of that, some requirements and propose some technologies that will then eventually end up in the Martian spacesuit design. So a little bit about the different types of missions. I kind of split them into three different categories. The first one is an operational research mission. So this is somewhere where resupply is feasible and you can get out reasonably quickly. So the International Space Station, there's fairly regular resupply missions. In addition to, it's possible to get home, relatively quickly. There's also analogous, operations on Earth. So there's analog missions, but there's also, I think someone talked about the Antarctic Research Station. So something like that. Well, I guess that's resupply for part of the year is not feasible, but so that's operational research missions. Deviating from that is more exploration missions. And so that's what NASA is right now working on preparing for. So the Exploration EMU is the suit that they created as their government reference design. And so it's kind of a shift. We're starting to think about breaking away from our low Earth orbit zone into deep space, where resupply is going to be more and more difficult to achieve, and coming back is going to take longer. So an historic example of this would be Antarctic exploration, where these explorers went out and everything they needed they brought with them. And something similar is going to happen with our extended stays on the lunar surface and then Mars initially. And then long term, we're going to start thinking about settling Mars. And that's again going to bring with it another paradigm shift. So instead of going out and exploring, the people who wear these spacesuits are going to be using them as pretty much protection equipment for their day-to-day job, similar to how construction workers wear hard hats. And so the type of spacesuit that will be needed for that will be, again, different. So a little bit about the operating conditions of Mars and how they vary from the places we've been. So I think we're all pretty familiar with the Earth environment. We have 1G, or 1 gravity. We have an atmosphere of that, relatively thick, especially compared to Mars. varied geology, and we're already on Earth. So if you think about the low Earth environment, it's very alien to the surface of Earth. So there's no gravity, well, no sensible gravity. There's no atmosphere, no geology, but you can get home fairly quickly. So the spacesuits designed for low Earth orbit, they're primarily contending with that lack of gravity and then the extreme conditions of a low Earth orbit. The moon's an interesting operation environment for a spacesuit, mainly because one, you're returning to a planetary surface, so your spacesuit needs to be more mobile. You're also dealing with this extremely abrasive dust. So because of the lack of atmosphere on the moon, there's no tumbling of the dust particles to kind of smooth them. So if you think about a river stone, stone's usually very smooth because it's been tumbled again and again. And that just doesn't happen on the moon. So you have very sharp, abrasive regolith particles, often with glass shards. So that's very problematic, but you're still fairly close to home. So moving on to Mars, you have pretty much roughly twice as much gravity as the moon. So that's going to come into play more with the suit architecture. You have a sparse CO2 atmosphere, so that's also going to come into play for the life support systems and some of the suit design. And regolith is going to still be an issue, but not as much as the moon. The real driver of a lot of the technologies is going to be that distance from Earth, where you're depending on the mission architecture, you might stay there for a month up to like 500 days. So that's one of the big drivers for the suit design. So from the operation environment and the Martian surface, we can kind of start to think about some of the requirements for a Martian spacesuit. So right now, the EMU, the extravehicular mobility unit, is rated for 25 EVAs. After that, it needs to be brought down to Earth to be refurbished. So if you're thinking about a mission that you're doing at least tens of EVAs, if not hundreds, there needs to be kind of a revolutionary advancement in suit durability that's going to be needed. Part of that is in situ repair or manufacturing. So if you're on the surface of Mars and resupply is at soonest months away, you need to be able to repair your suit. If you need to go out and repair something, you need your suit to be working. So you need to be able to do that on site. They're also likely going to be custom sized as a result of the long operating life, the repair technologies, and the performance benefits. These suits will also, like I said, have to contend with a fairly large amount of gravity. So they're going to be optimized for mass relative to some other things. I'll touch on that. They'll have to deal with Martian dust and the CO2 atmosphere. Okay, so just a note for designing for exploration and settlement missions. Thinking about Earth analogs, we need to kind of apply a lot of the lessons learned from Earth towards designing, these design products for space exploration. So what we want is a very simple, robust spacesuit. So you want to reduce the amount of parts and failure mechanisms for your spacesuit. You want to make it as light as possible. And then you want to kind of make sure that it fits into a mission architecture that's using it as much as possible and getting the most bang for your buck for every kilogram you send on its way to Mars. It's also going to need to be more durable, like I said. And then ideally, you want to design your spacesuit so at the end of its life cycle, you can feed it back and maybe recycle those materials to further get use out of them. So a little bit about the different parts of the spacesuit. When you think about a spacesuit, it's actually comprised of two main design elements. So there's the pressure garment system, which is the human-shaped balloon, roughly, pressure vessel, that the astronaut wears, and then they put on the portable life support system, which is that backpack that you always see them wearing. Yep. So now that we kind of have an idea of the requirements, I am now going to start going into the technologies that are going to be used to address those requirements. So like I said, the spacesuits are going to be needed to be used for tens, if not hundreds of EVAs. So suit durability is going to be a huge issue. So the EMU is a microgravity spacesuit, so it doesn't even have to contend with the planetary surface. On Apollo 17, those suits were used for 22 hours and they were beat up. So if you think about staying on the moon for a month, the suits are going to need to be pretty fantastic. And then let alone staying on Mars for possibly hundreds of days. Part of this longevity of the spacesuits is the technologies used in the portable life support systems. So for the spacesuit cooling, right now we use a sublimator in the EMU. So we have a block of ice that we then expose to vacuum, and then that ice releases, gas, and that's used to cool a water loop. But that requires distilled water. So there's a team at NASA that has developed the swimming, which is so it's an evaporator. So it's moving away from that sublimation technology towards an evaporative system that can use undistilled water. So it's going to be more robust, and ideally you can use in situ water as a coolant for your spacesuit rather than having to process that through a distillation process. Let's see. So in addition to that, there's also been a huge amount of development on the CO2 removal of the spacesuit. Traditionally, that's been done through a lithium hydroxide canister. The EMU now uses a metal oxide canister to scrub the CO2 from the suit's oxygen supply. But the issue is you need to bring those canisters with you. The lithium hydroxide, you need to replace it. And then the metal oxide, you have to regenerate it in your habitat or spacecraft. And then you're releasing that CO2 into the habitat's air supply. So what they've done now is they've designed something called the rapid swing bed system. And so that has two beds of functional material that absorb the CO2 from the air supply. And then when you contact those beds with vacuum or expose them to vacuum, the CO2 is removed, and you regenerate that bed, you prepare it for absorbing more CO2. And so you just have two different beds and you can switch between them. And the amazing thing about this is the longevity constraint is the mechanical components. So you can pretty much use this until the motor burns out, which is pretty good if you need to use it for 500 days. Okay, so that's so I'm more of a pressure garment subsystem, less of the portable life support system. So this is more my style. So more talking about the spacesuits. When we return to the moon and then we go to Mars, we're going to be operating on a planetary surface. So right now the EMU is a modular spacesuit, and it's assembled from a number of components. And you can kind of see here how underdeveloped the lower torso of the spacesuit is. So on the right of the red line, that's the upper body, pretty much from the waist up. And then from the red line to the left, that's the legs. And so if you think about all the complex mobility you need to have in your legs and compare that to the current suit's upper body mobility, you can see that our spacesuits are going to be a lot more complex when we return to a planetary surface. If you're climbing down into a permanently shadowed crater, you might want to have more options for your boots rather than small and large. Yeah. In addition to that, spacesuit fit's going to be more important because you're going to be doing more things with more limbs rather than maneuvering yourself about in microgravity with your arms. The thermal operating conditions are more difficult on a planetary surface. One, you're introducing new ways of kind of losing heat through contact with the planetary surface. The suit's also going to get dirty, and so that affects the optical properties of the outer layer. So you might have actually a higher thermal load if your suit gets darker due to contact with the regolith. The suit also will have to deal with the dust, falls, and impacts of the planetary surface. Another type of technology that I kind of touched on before is in situ repair and manufacturing of spacesuits. So I really think it's going to be key, at least, to be able to manufacture replacement components, if not the entire suit in situ. So I've kind of done some work on 3D printed spacesuits. So right now you would have to bring materials, maybe in bulk form, and then manufacture the spacesuit in situ. But ideally, you'd be able to synthesize these polymers on the planetary surface. But that's still work to be done. But I think this is going to be key, for initial Martian missions, but then once we get to a settlement, it's going to be absolutely necessary. So I also touched on this a little bit before. I think that the suits are going to need to be custom sized. If you look at the complexity of a modular system and then you extrapolate that onto a planetary spacesuit, I don't think you're going to get an adequate fit out of a modular spacesuit system, especially with the current trend of reducing the sizes available to the astronauts. One thing you can do with a 3D printed spacesuit is you can kind of build in that parametric resizability and allowing you to accommodate your entire astronaut population easier and more making it more bespoke. Yeah. One, yeah. What's up? Oh, yeah. One key difference between a lunar spacesuit and a Martian spacesuit is the type of dust that they're going to have to contend with. Like I mentioned, on the lunar surface, the dust is very abrasive. There is absolutely no tumbling. And so there are very sharp edges on the regolith particles. The spacesuits are going to be optimized to keep that dust on the exterior of the habitat or the inside volume of the space mission architecture. It's likely that they'll accomplish that through a suit port design, which is kind of one of the reasons you see NASA leaning towards a rear entry hatch for their spacesuits. On Mars, we won't have to deal with that very difficult abrasive regolith. So it's likely that our spacesuits will then be optimized more towards mass and less dust mitigation. So you might see a different type of architecture like this one, where it's just a simple dual planar entry, kind of on the rib cage, which allows you to accommodate a larger size range of astronauts while also reducing the overall mass of the system. One more thing that needs to be developed another thing that needs to be developed for a Martian mission is the spacesuit outer layer is going to be different. On the surface of Mars, there's an atmosphere, and with that atmosphere comes, again, more heat transfer mechanisms that you don't have in a vacuum. And so the type of insulation on the spacesuit is going to need to be modified somewhat. So there's been work done. I know Final Frontier has looked at using aerogel fabrics for an insulation material, and I'm sure there's more options. The MMOD threat level is poorly characterized on the moon and very poorly characterized on Mars. But it's likely that since there's an atmosphere, you're going to have less of a threat of MMOD because the secondary particles from an impact will not travel as far if a meteoroid impacts the surface of the planet. So the trades on the amount of design that goes into secondary particle impacts on the Martian spacesuit is likely to go down. And then the surface geology, I think I touched on that. It's the Martian spacesuit won't have to deal with that regolith, the sharp regolith. So one more technology that's kind of out there, that still might be applied sometime this century, hopefully, is mechanical counterpressure spacesuits. I think it's still very far away. I know there's some proponents of this technology here, but I think there's a lot of technical issues that still need to be addressed. One benefit is it does simplify the life support system. So your sweat is allowed to evaporate directly into the space environment. So it simplifies the cooling system of the spacesuit, and it does, in theory, allow a much greater mobility than a conventional gas spacesuit. And there's been work done. Final Frontier, again, now part of Paragon, developed a mechanical counterpressure glove that they entered into some challenges, and they've done a lot of fantastic work. Any questions?